Hello there, boys and girls of Physics Tube. Yeah, sort of wish. It'd be nice to have an actual place where you could actually make these arguments in some sort of disciplined way, where there'd be moderators. You know, disinterested parties who would decide whether somebody was being excessively snarky or rude, and, you know, the appropriate points off would be given, and flag would be thrown, penalty box, blah blah blah, and maybe we could all up our game just a little bit. As long as you keep the umpires unbiased, which is always tricky. So anyway, the chemistry is a brain hurt. I didn't block, even though he was typing absolute gibberish the other day. So it's just snarky shit this time. So, I deleted a couple of the comments. It was just being rude to other people who commented. And it was, it's just so unnecessary. And his arguments are so dishonest. And, but anyway, so he would start on this mass thing. Momentum is mass times velocity. And that's for big material objects. But mass gets a little complicated when you start talking about these little nuclear bits, as I'll explain. And I'm going to argue that, yes, okay, it's a legitimate statement, but there's other things involved in whether something is capable of doing work, you could say, or have energy. So momentum in and of itself isn't the only component that's relevant. Anyway. Photons have to change velocity in order to impart momentum. So this is his, axiom, his declaration of a truth. It's not a truth anywhere. Material objects change velocity, but they don't have to necessarily. There are kinetic interactions. Two steel balls can hit each other and they don't change their velocity. Anyway, this is one of the reasons your system violates this. 5th grade physics FFW, he says. So anyway, so like I said, this gets sort of to the holiday thing, and I guess I'll just do some talk on, just to clarify what my position is, so can be no possibility of misunderstanding, one would hope. Alright, so anyway, he says, so I said, do photons change speed? He says, no, they change relativistic mass, but only as a consequence of the Lorentz transformation. Just horseshit. Mass changes from what to what, I asked. It changes wavelength. See, so this is the tricky part. So now he's equated mass to wavelength. And this is the game they play, with the two-slit experiment when they do it with electrons, because electrons don't have a frequency. So they equate frequency to speed and decide that the faster the electron, well, we'll call that a higher frequency. And it's just bullshit. He says it changes wavelength. So I say, from what to what? It changes wavelength. So now you change mass into wavelength. So then he says, by the way, what does any of this have to do with tons? You brought it up. You said tons can't possibly function as photons. Right? I mean, that's why they're called tons, idiot. I mean, fool. I mean, insipid, crazy person. Why do you think they're called tons? They're named after photons. You don't understand that part? They go one speed, the speed of light. All the forces do that. Gravity, magnetism. You see? That's the relationship. Okay. Tons can't change mass. Why did I say they did? Where do they have to? Light can. Okay, so now he's saying light can change mass, right? So he just said it was wavelength, and now it's mass again. So light can change its mass. Light can in special relativity. But we're not talking about that, remember? So again, now he's saying that light, a photon, somehow can acquire more mass or have less mass, which I never heard special relativity does that to photons. but I think it's preposterous. So again, you can talk about wavelength being exchanged or changed, but again, I'm going to argue that that has really nothing to do with a strict energy equation. That just has to do with the fact that if I shoot 50 bullets in 30 seconds and I shoot 60 bullets in 60 seconds, the effect might be very different on the thing I shot with the bullets. So time often makes a difference in how you dispose energy, but it doesn't have anything to do with how much energy you started with. The gun fired the same amount of energy, whether it does it in 30 seconds or 60 seconds. The same amount of momentum. Light, according to you, doesn't carry momentum, so that was just a silly thing to say, in my opinion. It's like he didn't bother reading the web page. He's just a shit talker. And again, so I'm just saying to the people who are critical of the fact that there's a certain point where I just say block them. I mean, do I really have to type a response to that? I mean, do I really have to sit there and defend myself against an insane lie where I've never said light doesn't have momentum? I keep talking about how it has mass in one dimension. I keep saying it. There's other people complaining because I use the word one dimension. So I'll explain that again. I'm not saying the three dimensions don't exist. I'm just saying for a photon, it's as if the other two dimensions don't exist. It just doesn't do left, right, up, down. It just does forward. And it doesn't even really do back. So it only does 1/2 of one dimension. But that's all it does. All it's doing is like you closing your eyes and falling. I mean, you have this sense that you're just doing one thing. And that's what it's doing. One thing. And that's how they function. They only exist in one dimension at a time. They can't multitask in dimensions as we do. So light, according to you, doesn't carry momentum. So, ... I mean, it's just an amazingly stupid statement. Again, how could you possibly derive such a statement from anything I have said? I've said it doesn't carry 4 momentums, or 3, or 2. It carries 1. The direction it's going. Yes, I think I just pwned you again. So again, why should I have to tolerate such an obnoxious... He lies and then calls that pwning. I mean, it's disgusting. So I said his statement is insanely stupid. Lie. You say mass equals wavelength? Question mark. No response to that yet. But just an obnoxious pile of shit. So Mindless Marbles states conservation of quanta equals conservation of energy. Kind of okay. It also equals conservation of matter, I guess you could say. Or, but the tricky word is energy, right? In my opinion, it's a sort of a trick word. And I'll explain some of the tricks, but I mean, energy can be stored, and it can be, kinetic, released. But the trick is this whole idea of the energy and time. The time component of what becomes energy. The idea of the tipping point. The fact that I can throw 3 rocks, let's say, and if I throw them in the right sequence, I tip something over. I don't throw them in the right sequence, nothing changes. The two worlds look very different in terms of the energy equation. Now, it could be argued it's no different. The same amount of stuff went that way, and it hit with the same impact. It's just that it hit at the right time. So energy gets confused. And I'm not the one doing this confusion, right? I mean, this is what physics has done because electrons are sensitive to specific frequencies. And because they're sensitive to specific frequencies, their behavior looks more energetic. But it's not really. They had the stored potential. You just happen to hit the go button instead of the stop button. But the amount of energy is the same. You just released potential energy. Or you didn't, based on how often or quickly you hit something. So it's really not, although the electron is reacting, there's really nothing There's no extra energy. So ultraviolet light doesn't have extra energy. It might have extra tons because it's a tighter frequency. In the same amount of time, the two kinds of light, infrared and ultraviolet, are going to have, the ultraviolet will have twice as many momentum bits in it. So there's twice as many bullets in the gun. But strictly speaking, ton for ton, they have an equal energy component. Bullet for bullet, they're just bullets. Alright, conservation of direction equals conservation of momentum. That's pretty good. So, I mean, generally speaking, that I agree with those equations, those equalities. And maybe that'll clear something up for Hoffaday, I don't know. But clearly, when a photon gets released, it isn't pushed out of its circumstance. It's released out of its circumstance. It was potential photon, and it became actual photon. And it's not pushed based on momentum. It's pushed, it's released based on just circumstance. It's making an exchange. Now, the idea that there would be some connection between how much stuff you have going in a particular direction and the idea of giving away energy in that direction. So yes, if I have 1,000,000 gold coins and 1 silver coin, it's more likely I'll give away the gold coins, kind of a thing. So it's more likely I'll release a photon in the direction I have more energy in, more momentum in, more directionality in, that I've stored in. But as I pointed out with the stuff in the, when something is spinning, once something's spinning, it's essentially collecting momentum in all directions, and it can release it all in one direction through these conversions. These free conversions, by the way. The interactions, the kinetic interactions, don't consume any third party. They don't need a catalyst. They don't need some other energy to make the transfer of energy possible. So when two things collide, their exchange is free in the sense that the collision is just an exchange. Alright. I think that's a fair characterization, right? Yes, I'd say it's fair enough. But like I said, the word energy is, physics has made a mess out of that word. I didn't make a mess out of it. They made a mess out of it. So anyway, I'm skipping these meaningless comments. So anyway, this one guy said, I can't imagine anything that isn't 3D. It seems that anything can only move in one direction. Well, the whole point of acceleration is they're combining directions. That's the whole point of the thoughts experiments, talking about a baseball on a bus, is that it's combining directions. So while it's accelerating, that's not true. And most things are always in some sort of accelerating frame, in the sense we're getting pulled by gravities of Venus. You know, it's accelerating us just a tiny bit, but it's there. Yeah, I don't know how to help you. Can only move in one direction. The things, the littlest bits, can only move in one direction. I mean, you don't see yourself jiggling the atoms inside of you, but they are. You don't see yourself not moving, you know, pretty solid. You don't see bullets vibrating, but they are. I'm just saying nothing's moving as straight as it might look. It's just a fact. Even if affected by more than one force. So again, things move in one direction at a time. But the point is it's almost like a bullet in a gun. I mean, it could be bouncing off the sides. You know, you can understand that, right? It's like the light argument with Hoffaday, right? So let's say you had a light clock and you're moving, and so the light's bouncing off the two mirrors. The idea would be when it's going this way and hits the mirror over here, it's imparted force, and so when the photon is free again, right, it's in between the two mirrors, okay, it's not affecting anything. It has no meaning in the universe. but when it hit the mirror, it exchanged force. It exchanged force with the mirror. It said with the mirror, you take this direction, I'm going to take this direction from you. So now the mirror has some of that. So the spaceship moves a little bit that way. And then when it hits the other mirror, it's going to make the opposite exchange. It's going to say, I'm going to exchange this for that. And so that mirror ends up going that way up just a little bit. So yes, at any one moment, frozen universe, you could say everything has a straight line trajectory, but everything, I mean, the apple is to the earth as the atom is to the apple. The stuff is really tiny, and it's bouncing a lot inside of you. It's doing a lot of ricocheting. What's the difference between dimension and direction? Yes, I'm ignorant. There really isn't in the three dimensions. So when people say there's a time dimension or some other kind of dimension, well, that's bullshit. But there's no distinction. It's just that there's also, everything has its own gyroscope, so to speak, of defining forward, left, right, up, down. So everything can have a different. So you can have an absolute standard for what's up and what's down, what's left, right, what's forward, back, and you can have an individual one. It just depends on what you're doing, which one applies. All right. Let's see. Was watching an artist the other day, Desperado or something. He said artists' minds are continually imagining. Oh, he's talking about my less than pleasant pre-sleep images. I can't deal with all the points raised here. Yes, I don't want to get on the mindless marbles. Thinks he has something on the lensing subject, and I went to the documents and they're pretty much nothing. Opinion pieces. It is interesting that they did launch some kind of satellite 4 years ago that was supposed to get the most accurate data ever on the location of every star, and so any lensing should be detectable, in the sense that whatever they're seeing that's getting lensed, they should be able to tell. And I haven't heard any of that being released, and they've had 4 years of data now, and maybe they didn't find what they were looking for. But anyway, I haven't researched that. Alright, so I don't think there's anything else here that I have to get to. Focal points. Yeah, you don't really have to worry about focal points at very long distances, because there's a million of them. Okay. Yeah, I think that's it. Alright, so how to do this, how to start. Alright, well, as I've stated before, there's only essentially two kinds of interactions. I did think of something else that was a little bit curious. I haven't really thought about enough to fix the problem or to go through the whole spiel, but I had previously talked about how the strong force can be understood, the force that keeps protons together, as just being the function of the neutron, in the sense that it has this electron that it can put between it and the other proton. And so then you end up with a situation where all the red force leaks out of the electron that's bouncing between these two, so there's no pressure between them anymore. And the thought I had was, once you release all this red pressure, if I kick this electron out, I'm sorry if I wasn't focused on this, if I kick this electron out, then there's no tons between the two red things, and there's plenty behind, either side, and so they're going to be pushed closer together. Because with the electron, there was some break, and the break would be that a red could still go inside the electron this way and come out this way. So you had still some break against a complete vacuum. But if I kick the electron out, there's no vacuum, and the two protons don't really have a choice but to slide right into each other. And so that's a curious fact, right? That the things with the strongest, the same would be true if there were two electrons between a proton, on either side of a proton, and I kick the nucleus out. The two electrons, theoretically, don't have a source of anything between them to be reflecting back and forth. There's no way for it to get in there, by my theory. So it's just kind of curious. It's something I'll have to deal with, obviously. But that could be another mechanism that creates these other particles they keep seeing. But that was a whole nother subject. Is that it's almost like a whole nother subject. It's almost like the difference between physics and chemistry is the difference between the identification of the eccentric and abstract particles is almost a whole separate field of physics, in the sense that there's that data is requires a whole kind of you have to get familiar with what kind of data they're using and what they're seeing, because they're not just taking it's not just pictures kind of thing. I mean, it's nothing obvious that they're building their understanding out of, and I would argue that that's a real flaw, is that nobody can really scrutinize the determinations they make about what they're going to call things and what things are and how they identify them and what mass they have, because they don't have any tools that are really good at doing any of that. It's really hard to measure charged particles, their mass. Really difficult. And they don't really say that. They talk as if they know something, and they have sort of an idea, but that's as best they could do, is say, we have sort of an idea. But, to scrutinize it, is a little difficult, and especially even on the internet, it's hard to get the raw data that's used to draw their conclusions, where you could understand, this is where they made a mistake, something like that. Anyway, that's a whole different subject that I'm going to have to deal with eventually, I know, but it's just that it is kind of you can't really access it because the raw data isn't there. So anyway, it isn't easily accessible. Alright, that's why like a physics YouTube would be very good, is that people doing that kind of work could say, hey, this is what I do every day. This is the stuff that I look at, and this is how I identify these little abstract bits, eccentric bits, however you want to describe them, ghostly particles. Anyway, all right. So yes, the basic idea is that there's two things. There's these little matter bits, and let's just restrict it to protons and electrons, and we'll say that a neutron is a proton and an electron very close together. And the little matter bits, they have some kind of mass, but the whole point is they move, like I said, I don't know precisely, but I'm saying they tend to move a lot with very little energy. So let's just say you hit an electron with a photon. The electron will move. So it can't have a very heavy momentum barrier. I don't think it can be as massive as they think it is, because the photon is so much less massive, in a sense. It's just a force bit. But the point is that the matter bits and the force bits, so the force bits don't interact with the force bits, the matter bits don't interact with the matter bits, in the sense that if two matter bits get close together, there's usually going to be a force bit between them, and it's going to be force on matter. It's never really going to be matter on matter, in spite of what I just said about the proton dilemma. I'm sure there's an answer to that, I just haven't thought of it yet. So what you can think of it as is that the force bits just use the matter bits as catalyst. The force bits are the things getting separated by the proton and the electron. So let's understand that there's two kinds of field energy, two kinds of field momenta, quanta, photons, tons. All right, there's black ones and red ones. And when a red one hits an electron, it does a right turn or a left turn or an up or an out or an in. It goes in one of those two dimensions, in the four directions of those two dimensions. And when a black one hits the proton, it does the same thing. It goes in some other direction, one of the four directions, one of the four 90-degree turns, perpendicular. And when the same color hits, it does an exchange that's more obvious in the sense that it will essentially do the reflection thing. The red bit will leave and the red bit will change direction. One that was going, say, this way will flip to this way and go to that direction. So this thing has essentially changed its percentages. Say if this was full of just little bits, it changed its percentage, so it has an extra one going this way. Now, how many? See, technically, these things could have zero mass, in a sense that you hit it with a red bit and it goes the speed of light away. That would indicate that it had no mass, that it just did the interacting. But clearly they don't go away at the speed of light. They go away at some percentage of the speed of light. And once I know that percentage, then I guess I could say there's 100 of the little mass bits inside of here, or 1,000, or whatever the number would be. But you could just kind of tell by hitting it with a photon and seeing how much it moves. That'll tell you something, how fast it moves. But that's really hard to do. Again, you know, seeing how fast a proton moves in the first, as it's coming out of the gun, so to speak, right at the start, really hard to do. It's easy to see it, you know, when it's already losing its momentum, its speed, and it will lose it, as I've explained before. Protons and electrons aren't capable of carrying momentum, in the sense that if you shoot one into space, it won't keep going. It'll stop. Alright, I think. I'm pretty sure. It has to be pushed by a force. Something has to keep on nudging it along. A constant field, like the sun. The sun produces all these photons, and it's also producing a bunch of other kinds of radiation. And that radiation pushes electrons all the way out here, and it ends up being the aurora borealis and all that kind of crap, because it's pushing the heavier thing. It just keeps pushing them because it has a whole bunch of little tons that just keep hitting it and saying, keep going, keep going, keep going, keep going. Alright. Right. So that's the one uncertainty is exactly how reactive are protons and electrons to one quanta of interaction. How much do they move because of it? And that would also affect this fact where I've pointed out before that when this exchange happens, and that's what it is it's an exchange. The black arrow goes in, the black arrow goes this way, and a red arrow leaves going, well, it gets captured going this way. So it captures some momentum this way. So this stays in here. So that's the exchange. The black hits something, a red arrow going this way. So the red arrow was going this way. The black arrow hits it. The black arrow goes this way. The red arrow goes this way. So it's always an exchange. It's always an exchange. So we just draw exchanges. And then you'll get my print. So this is what's always happening. Okay? The black thing hits the red thing goes this way, the black thing goes that way. So, although it looks the same in the sense that the same thing is happening, a thing goes this way is still going this way, a thing going this way is still going this way. The thing that happened was the colors have changed, which is significant. Alright, so the argument is that all the momentum is in the force, and as pointed out, the electrons don't like each other because any force that gets between them, because you sort of understand, because it reflects, it just keeps reflecting, and it keeps reflecting, and it keeps reflecting. And so as you bring the two electrons closer together, this frequency gets higher and higher. And you can kind of understand that because of that, the pressure gets higher and higher. The pressure to go this way gets higher and higher because of these impacts. These exchanges are creating an opposite but equal reaction away. I mean, it's, you know, perfectly sensible. That's what the reflection will cause. And so that's where frequency sort of starts getting important, because now what we're saying is that distance is energy, in a sense. And so that complicates the equation, because it doesn't seem like that should be able to make something that should make a quanta. It doesn't really make one. All it does is take advantage of the one that exists and multiplies its effect. So the more often a quanta interacts with matter, sort of defines its momentum, in the sense that the more it's hitting stuff, the more it's doing stuff. The less it's hitting stuff, the less it's doing. So that's where the word energy gets confusing, is because you haven't really, it's hard to describe what exactly the energy is in merely moving two things together. Now, it takes energy to do it. So obviously, if I want to push two electrons together and there's a certain amount of pressure here, I'm going to have to hit with more pressure than exists here to push them closer together. So in that sense, the energy is conserved because I have to use more hits to create the higher frequency. So a higher frequency requires an investment of energy to create. So then you can sort of understand that, okay, it's not that the blue light has more energy, in the sense that the tons don't have more energy, but the fact that they are at a higher frequency means the only way they could have been created was by something pushing something and creating more pressure, higher frequency. And that's that higher frequency, when released, okay, that still has the signature, so to speak, of the fact that it was made by a process that required quanta to hit something, more quanta to hit something, to create the pressure, to create the higher frequency. So that's why electrons are sensitive to it. It's because they essentially create that. That's the formula for how they interact with the force. It's all about this pressure equation. And the pressure is dictated by how often you're getting hit. And how often you're getting hit is sometimes going to be dictated by how far away the other thing that might be reflecting is. So the closer it is, the more you're going to get hit. So anyway, it does just make it a little more complicated than just saying arrow in, arrow out. Because it's not the arrow itself that has the power, in the sense that it's the combination of having the movement and then having the distance. When you shorten the distance, you get more impacts. It's just a fact. I mean, it seems more energetic. If you just do a simple thing, you move the two things, and you have automatically more reflections. And with each reflection, you have a force, an element of movement. Alright. So that's why I'm uncomfortable with the word energy. It's because some parts of it are explicit, quanta, and then some parts aren't explicit, quanta under pressure. That's more it's more of an ambiguous form of energy. It's only understandable as a time equation. You can't see it as just two states. And you look at the two states and you say, what state are the two universes in? 5 seconds apart. And you just freeze it. You can't see that energy in that circumstance. You have to see it in a timed equation where you count how much something goes back and forth. How often. Okay, so yeah, that's sort of the major thing I wanted to get to. So, photons, in my opinion, are all the, like I said, the force is doing all the work. So that's, I guess, another thing is one of the key points I want to make, is that you can almost think of the matter bits as being just catalysts. They're just things that make it possible for a force over here and a force over here to interact. The matter is what makes the two forces fight each other. Without the matter, they go right through each other, like light beams going through each other. It's the matter that gives the light capacity to fight with each other. So if you had red light on one side and blue light on the other side, put a piece of matter in there, and then the blue side can win because it's more tons in the same amount of time. So anyway, yes. So the only other point to make, I don't see how, anyway, this looks to me very conservational. I mean, I'm not saying anything here where anything gets loose. And so, photons, as I stated with the example of the moon, there's always going to be some, you'll see it. If you can go out and find the exchange. So it's always an exchange. So that's another key word. So I guess I should write down some of this stuff. But you can always find, if something's going this way, something has to be going this way. And it'll be somewhere. It doesn't have no effect. It has an effect. So but that doesn't give you the intuitional right to say, well, because something's moving in a direction, that means everything inside of it's moving that direction. And so it can only shoot things in that direction, because that's not true. And especially something like light, which is a tiny percentage of the stored energy that's in a piece of matter. The whole nuclear argument. You could just take the top head of this pin, and if you knew how to make it properly radioactive, you could blow up a city with it. The energy that's in there. Look at the number of little bits moving the speed of light. If you release them from their bonds, from their traps between these matter bits, if you release them from it being trapped inside the atom between the electron and the proton, see, that's how people don't see. When they look at an atom, all they see is electron and proton and neutron. No one draws a picture with all the energy that's tying those things together, that's flowing between those bits. And it's that energy that's released in a nuclear bomb. And when it's released, it pushes all the little bits in all kinds of directions. They're not in circles anymore. So the idea is, as I've pointed out before, I think somewhere in the nature of the electron, the neutron and the proton, there is the relationship that essentially creates the circle. Where you have a bunch of, you have right turns, and they all add up to or left turns, and they all add up to a square, or in other words, a circle. And once you have that, you have the trap. And that's where you can just fill the trap full of energy moving in these flows, in these directions. And the point is if you break the trap, you break open a piece of it, then you can understand that everything that's trapped in there flies out. And, so the point I'm trying to make, though, is a photon is a tiny percentage. Photon, the electromagnetic spectrum even is a small percentage of the energy inside or in the universe. Tiny percentage, and it has been converted into photons. Tons moving at a frequency. So again, I've already done this, but I'll do it one more time. Gravity is just these little bits, so they're all the same bits, same exact bits. And gravity just means there's no frequency, so they don't come at a steady frequency, and they're two colors, red and black. Well, it's no point in random, red and black in random order. Magnetism is no frequency, and but the two colors are segregated. So red and black are filtered by the magnet, the magnetized material, and so now the black bits all come out one end, and the red bits all come out the other end. And what's the other thing? And light. So light is these things at specific frequency, and I believe they're black. They affect electrons and give them momentum, or they impose pressure on electrons. So I think they're electron quanta. So I should come up with a name instead of red and black. I should finalize this into like the proton tons are proton tons, and the electron tons are electron tons. So that's not going to work. But yeah. So that's it, though. But the point is that only a tiny percentage of this energy, the gravity energy, the stuff that moves planets around, is in the form of light. But light's the same stuff. It's just been converted into having a frequency. It would have been gravity if it didn't get rearranged by getting trapped and then released at a specific frequency. It was gravity before it became photon. Alright, none of this is created. Like I say, it's just filtered, and that filtering is just the key to this whole thing. You just have two types, and then you have a mechanism to filter the two types, and the two types affect the two things, the two pieces of matter, differently, and that's it. That's all the complexity is made out of that simple function. Alright, so the other thing I wanted to make clear, which I have stated clearly, but I'll just do it again, just to separate myself from Lesage gravity, because I do have an actual, a more detailed description of how gravity works. And so the point is I have to draw a little bit here, that it's not just some kind of like pressure thing. It's not as simple as just saying stuff hits it, particles hit it. Because what's really happening is that it's exchanging the momentum. So what's happening in gravity is this thing, even just randomly, could take in one more red arrow. Say a red arrow comes in, and it absorbs that arrow and releases, exchanges. So it doesn't exchange with an arrow going this way, and so it keeps it gets rid of this red one this way, and it keeps the black one going this way. However you want to look at it, doesn't matter. It keeps this positive arrow, and it gets rid of something going this way, or something going this way, or something going in one of the other 5 subdimensions. Each dimension has 2 sides. And so now it has more momentum in this direction. It absorbed something that would have hit here. So now this is busy inside of this giant thing, moving every tiny little bit So the force of this thing is essentially going through all the traps, all the stuff here, and it's giving it a slight bias in this direction. So this could be a gazillion particles. And so you could think that, yes, it's taking an incredibly long path because essentially the force has to travel all of these traps. It's a huge, gigantically, crazily long path it's taking. So it's stuck in here. It's part of this now. And the point is it doesn't go here. So that arrow never gets here. And so because it doesn't get here, there's an imbalance between these two sides. There's more pressure here than there is on this side. So there's less stuff getting reflected back, if you think about it as a reflection. Less stuff is getting reflected back, and so it's going to have the hangover of more of this stuff is end up going to get absorbed by probability. It's going to have, this is going to have more stuff going this way, is going to do more interacting than stuff going this way. And all the interactions are going to be the same. Stuff leaves sideways or stuff leaves back, reflections. But those are going to be the two choices. So more interactions are happening from the force coming this way than the force coming this way. So because there's more interactions, this thing is going to accept an arrow going this way. And it's going to get trapped inside of here. And so that's what I mean by inductive. One thing moves towards the other, then the other one reacts by moving towards it. And now that this thing ate that extra arrow, that means this arrow trapped in here, that's causing a little bit of momentum this way, isn't going to hit here. And the same scenario is going to happen. Now there's going to be more pressure here than here. There's going to be more probability of interaction from the force coming this way. So the same thing's going to happen. This is going to move forward towards it. And that's gravity. And that's Einstein's gravity, because unlike Galileo, who did the M1 and M2, G over R squared or whatever, it's not just a two-mass equation. It's two-body equation, and the two are doing as Maxwell. I mean, Einstein was just another version of Maxwell applied to gravity, or you could say vice versa, but it's just accounting for the fact that this is inductive. This doesn't, you don't just have gravity, you induce it. That's why something else has to be in the equation, because it has to induce the gravity. It has to make this thing have a reason to come towards it, to move. So the point is that it's an absorption of force, and clearly as the body starts moving and gaining velocity, the entire mass, that means it's collected a lot of force going this way. And I'm arguing that that's in the form of a trap, in the sense that the quanta bits going this way have a lot of matter bits between them. So they're just pushing the matter bits and creating that pressure. And this circle, to complete the square, okay? So this is the trap. And here, and so here's the trap. And the trap has a lot of mass on this side and no mass on this side. So you can see that the trap keeps pushing lots of matter, and it's not pushing any matter on this side. So when this body has all of this mass here, the mass is convertible into these tons, in the sense it's convertible into action on the ton. So if the mass is moving, it can push a force. It will reflect the force. So it has lots of reflective capacity here. And so when it gets, so it has essentially stored all of that, this arrow direction, in the form of the matter being pushed by it. And when it collides with something, all of that force of the matter bits, the compression they'll cause, the fact that there'll be an electron and an electron, and this electron is being moved. And so it's going to get close to this other electron, which is going to cause a hell of a lot of pressure between those two. And so all of the force has been collected as a velocity, and when it finally gets to when the Earth crashes into the sun, let's say, or the asteroid flying in, you'll see the effect of all that energy being released. because it collected it. That's what the velocity represents. The velocity represents collecting the gravity. It collected the force, held it in a slower... See, if the force went to the sun without going into the earth, it would have got there really fast, the speed of light. But the earth isn't going to go nearly the speed of light. It's going to go a hell of a lot slower. And so the force is going so much slower. But it's eventually going to get to the sun. It's just taking its time getting there. And it's that time difference that's all the difference. It stored a whole bunch of stuff from yesterday, and when it finally gets to the sun, it's going to release yesterday, the day before yesterday, the day before yesterday. It's going to release a whole bunch of days of collected velocity, of collected force that didn't get to the sun. I think that should be understandable. Alright, so yeah, this isn't really a overview video, but it has components. But yeah, I mean, it's each bit, each concept, you could spend a whole lecture, a whole, lots of time on it. You could spend more than that. You could spend a few hours going through all of the possible scenarios. So it's not as simple as, it's very simple, and I'm attempting to make it understandable. It certainly seems perfectly functional to me. It's perfectly consistent with physics. So I'm just trying to understand why people seem to have these insane misrepresentations of what I'm saying. Besides their own being a belligerent asshole, I can't understand how I can make this clearer. And it's based on just such a simple mechanism. It's just that even when you have a simple mechanism, the permutations are exponential, because you can have a circle inside of a circle inside of a circle. I mean, it can get complicated. The path of this like I said, this trap I talked about, the trap could be incredibly complex in the sense that it could go left first and then goes right over here, and then it goes left again, then it goes right, and then it goes left, and it can be an incredibly bizarre trap in terms of the directions that it's going. But the point is, it's a trap. The point is that the force doesn't get outside of the material thing that's holding it. And that's the point. And that's the nature of the storage of energy, is trapping it. The energy is the ton moving, and matter allows it to be trapped. Okay, matter bits. Okay, well, that's good. I don't think I'll gain anything by going any further, so we'll call it a day, and try again tomorrow.